Hello everyone. In this very video we are going to be looking at equilibrium constant Kp. The last video we saw Kc, but in this particular video we are going to see the calculations, all the calculations involving Kp. Now Kp is the ratio of the partial pressures of the product to the partial pressures of the reactant. That's of an equilibrium reaction. Now each pressures are raised to the power of the coefficients of the substance in a balanced equation. Okay, so we look at this example. Given a reaction, this is an equilibrium reaction, A plus B giving us C plus D with their coefficients, small letter A, B, C, and D. Now the equilibrium constant is just is written like the concentration constant, that's equilibrium constant Kc. Kp is written like Kc, but the difference is that Kc is in terms of concentration, but Kp is in terms of pressure. So if I'm given this, remember we are dealing with only gases or aqueous solution. So equilibrium constant is only concerned with gases or aqueous solutions. The equilibrium constant is given as Kp equal to, you see, the pressure of C raised to power C times the pressure of D raised to power D, which is the number of mole. That's for product all over the reactant, divided by the pressure of A raised to power A times the pressure of B raised to power B. Okay, that is when given the partial pressures. Okay, now this can also be summarized, because sometimes in your questions you will not be given partial pressures, you're going to be given mole fractions. I'm going to explain what that means. So the whole of this can also be written as the mole fraction of C times the mole fraction of D divided by mole fraction of A times mole fraction of B times the total pressure of the system. The total pressure raised to power C plus D, that's the difference in the number of moles. C plus D means the total number of moles of the product, minus A plus B means the total number of moles of the reactant. Okay, let's move further from here. Now, your PA, PB, PC, PD are actually partial pressures. The partial pressures of gases A, B, C, and D. Now, there are things to note. The first thing to note here is that the total pressure of a reaction is equal to the sum of the partial pressures of the individual gases. So if we, like in the example above, we have gases A, B, C, and D, the total pressure of the system will be pressure of A, partial pressure of A, plus partial pressure of B, plus partial pressure of C, plus partial pressure of D. Of course, you know that's according to the law of Dalton's law of partial pressures. Then the second thing I like us to note is that the partial pressures of individual gases is equal to its mole fraction multiplied by the total pressure. That is, the partial pressure for A is equal to the mole fraction of A multiplied by total pressure, where this is the mole fraction of A. The mole fraction, now, the formula for mole fraction is the number of moles of A all over the total number of moles. That means Na over N total. Let's see an example here. The first thing we're going to look at, there are 4 cases actually. We're going to look at calculation of Kp given partial pressures, if the partial pressures are given. Now let's see the first example here as a question. Given the equilibrium constant Kp, give the equilibrium constant Kp expression for the reaction below. We have to give the equilibrium constant. Okay, so at this point, look at, first of all, you notice that they are all gases. So we can write that the equilibrium constant Kp is equal to the partial pressure of water raised to the power of 2, that's the number of moles, divided by the partial pressure of hydrogen raised to the power of the number of moles, which is 2, times the partial pressure of oxygen. Okay, that gives us the equilibrium constant Kp for the reaction. Now let's look at another example. In this case here, we are given values. It says, what is Kp for the reaction given that the partial pressures at equilibrium are, the partial pressure of hydrogen is this, 0.9968, and the partial pressure for oxygen is this, 1.1058 atm. Now, but first of all, let's look at the reaction. You see, but you can notice that there's a difference between this and the previous one. Here, both hydrogen and oxygen are gases, but water here is a liquid. So how do we go about this? So it means that my equilibrium constant Kp will be equal to 1 over, why is it 1? Because this is a liquid. You don't consider liquid in writing equilibrium constant. You only consider gases and aqueous solutions. So this is 1 all over the partial pressures of hydrogen raised to power 2 times the partial pressure of oxygen. Okay, so which is going to be 1 divided by the partial pressure of hydrogen in the question is 0.9968, so raised to the power of 2, then multiplied by the partial pressure of oxygen is 1.105. Very good. So with that, when you calculate, you are going to get, it's going to give us 0.908. Now we are going to look at calculation of Kp given mole fraction. So how do you calculate Kp if you're given mole fraction? Let's see the first example here. The mole fraction of a closed vessel of the following gases are 0.2, 0.3, and 0.4 for chlorine, oxygen, and Cl2O5. If the following equilibrium is established with a total pressure of 3 atm, we are given total pressure. What is Kp? Okay, so that's the equation for the reaction. And we were given, I gave us, okay, so we'll look at calculation of Kp given mole fraction. Now, the mole fraction of a closed vessel of the following gases are 0.2, 0.3, and 0.4 for chlorine, oxygen, and Cl2O5. If the following equilibrium is established with a total pressure of, when the total pressure is 3 atmosphere, what is Kp? Okay, so this is the equation for the reaction. And from here we can say that the Kp for this reaction is equal to the mole fraction of chlorine raised to power 2, that's the number of mole, times the mole fraction of oxygen raised to power 5, then divided by the mole fraction of Cl2O5 raised to power 2. Now that's not all. We are going to multiply this by the total pressure, P total raised to the power of the difference in the number of mole of the product and the reactant. That means the product, the number of mole here is 2 plus 5, then minus the reactant here is 2. Okay, remember this is the formula you use whenever you are given mole fraction. So if we continue here, this is now going to be equal to the mole fraction for chlorine in the question is 0.2, so we have 0.2 raised to power 2 multiplied by 0. For oxygen is 0.3, so that's 0.3 raised to power 5. Now divided by, for Cl2O5 the mole fraction is 0.4, so 0.4 raised to power 2, then times the total pressure in the question is 3. So 3 raised to power what? 2 plus 5 is 7. 7 minus 2 is 5. So times 3 raised to power 5. So when you multiply this, it's going to give us our final value. You can do that and send me the answers. Okay. Now we go to a next question. Here we are given, consider the reaction below. Here nitrogen combines with hydrogen to give us ammonia. That's the Haber process. The mixture of gases at equilibrium contains 20 moles of nitrogen at equilibrium. Remember, note the word at equilibrium. 20 moles of nitrogen, 60 moles of hydrogen, and 20 moles of ammonia at a total pressure of 200 atm. Calculate Kp. Okay, before we can calculate Kp, we should, since we are given the number of moles, we can easily find the mole fraction. Now, solution here. Here we can say the mole fraction for nitrogen. We can say the mole fraction here for nitrogen is equal to the number of moles of nitrogen is 20 all over the total number of moles. If you notice, is 20 plus 60 plus 20, 20 plus 60 plus 20, and that is going to give us 20 over 100, which is 0.2. Now the mole fraction for the next gas there is hydrogen. It's going to give us the number of moles for hydrogen is 60, so 60 all over 100. That would give us 0.6. 100 is the total number of moles. Then for ammonia, the mole fraction for ammonia is going to be the same 20 all over 100, which is equal to 0.2. So at this point, we can calculate the Kp. So here, your Kp is going to be, according to the reaction, is going to be the mole fraction of ammonia raised to power 2 divided by the mole fraction of nitrogen times the mole fraction of hydrogen raised to power 3. Okay, remember the whole of this multiplied by the total pressure raised to power the difference in the number of moles. The product is, the total number of moles in the product here is 2. Then minus the total number of moles in the reactant is 1 plus 3, making it 4, altogether 4. Okay, if we substitute the value here, it's going to be okay, so that is going to give us our Kp now is going to be, the mole fraction for ammonia is 0.2 raised to power 2. Now divided by the mole fraction for nitrogen is 0.2 also. Then multiplied by the mole fraction for hydrogen is 0.6, so raised to power 3. Now multiplied by the total pressure. The total pressure from the question is 200 atm. So we have 200 raised to the power. The difference in the number of moles here is 2 minus 4. That's minus 2 raised to power minus 2. Okay? You can calculate that and send the answers to me. So we're going to look at calculation of Kp given initial pressures, when initial pressures are given. Now we see an example here. Chloromethane, which has been used as a refrigerant and a local anesthetic, can be made from the following reaction. So we have this reaction here. Now Kp, the Kp for this reaction is 5.9 times 10 to the power 3. Now you can say 5,900 at 120 degrees Celsius. If enough methanol and hydrogen chloride are added to a container at 120 degrees Celsius to yield an initial pressure of 0.75 atm for each, what will be the equilibrium pressures of all the reactants and products? Okay, so we go by the reaction. Here we have CH3OH reacting with HCl, giving us CH3Cl plus water. And you should note that they are all gases. They are all gases. Okay. Now, in this case here, we are given initial pressure actually of methanol and hydrogen chloride. Now, in this case here, we can use the ICE method to break this down. Now remember what I means. I means the initial concentration. So the initial concentration for this is 0.75 atmosphere. For HCl is also 0.75 atmosphere. Now, but for this and this is 0 because at the initial the products are not formed yet. Then C here talks about the change in concentration. Here the change in concentration is minus X. Here the change in concentration also minus X, like the other video. If you don't understand this, look up the video on equilibrium constant Kc. It was well explained. So change in concentration here is minus X, minus X. The minus sign is because the concentration is reducing, in this case the pressure is reducing. Then here the pressures for these two would increase by X and X. The number of moles is 1, so just X and X. So we now have E. So what is our E here? E is the equilibrium concentration. The equilibrium concentration for this is adding I and C. So for here is going to be 0.75 minus X. For here is the same thing, 0.75 minus X. Then for here, 0 plus X is X, 0 plus X is X. Now here we can now go on to write our expression for Kp. Kp here will be the pressure of chloromethane times the partial pressure for water, divided by the partial pressure for methanol times the partial pressure for HCl. None of them have number of moles. They all have number of moles of 1. And according to our equilibrium pressures now, we are going to get X multiplied by X divided by 0.75 minus X times 0.75 minus X, which according to the question we are given that the Kp for the reaction is 5,900 or 5.9 times 10 to the power 3. Okay, if we continue with that, you see that X times X here is going to give us X squared divided by this is going to give us 0.75 minus X all squared equal to 5,900. At this point, we can take the square root of both sides. We are going to get X over 0.75 minus X is equal to square root of 5,900 is about 768.1. So at this point, we'll cross multiply and solve for X. When we do that, we are going to get X to be 0.749. Okay. Now the question we are asked to find is the partial pressures for each of them. Now I would like to say here that the partial pressure for both CH3Cl and water is equal to X, and the value for X here is 0.749. But the partial pressures for methanol and HCl is 0.75 minus X, which means 0.75 minus 0.749, and that is going to give us 0.001. Okay, so that moves us to the next thing. Okay, so we are going to look at calculation of Kp given degree of dissociation. At 25 degrees Celsius at 4 atmosphere, PCl5 is 10% dissociated. Calculate the Kp for the reaction. Now we are going to start by considering the initial amount. In this case, whenever you are given degree of dissociation, you can assume that the initial mole is 1 mole, and of course this is 0, 0. Then the next is to find the equilibrium concentration, the equilibrium mole. Okay, here is dissociated by 0.1%. I mean 10%. 10% actually means 0.1. So meaning that at equilibrium, this would be 1 minus 0.1, which is actually 0.9. Then while this will increase by 0.1 and this will increase by 0.1, since it is just 1 mole. If there were moles, we would have multiplied by that number of moles. So this is what we have. So this is the mole distribution of PCl5, PCl3, and chlorine. So the next here is to find the mole fraction, because we are not interested in moles. We are actually interested in mole fraction. Now, and to find mole fraction, we must find the total number of moles, in this case, which is 0.9 plus 0.1 plus 0.1, altogether gives us 1.1. Okay, so we can say that the mole fraction of PCl5 is equal to the number of moles of PCl5 all over the total number of moles, which means 0.9 all over 1.1, and that is giving us 0.82. Okay, the mole fraction does not have units, so the mole fraction of PCl3 is equal to the number of moles, which is 0.1 all over the total number of moles, which is 1.1, and that is giving us 0.09. And that is exactly the same for chlorine, 0.09, since the number of moles is also 0.1. Okay, so we use our formula for finding Kp. We say when we are given mole fraction, the Kp in this case now will be the mole fraction of PCl3. There is no power there because no number of moles, times the mole fraction for chlorine divided by the mole fraction for PCl5, multiplied by the total pressure raised to the power of the change in number of moles. The total number of moles for the product is 1 plus 1, which is 2. The total number of moles for the reactant is 1. So 2 minus 1 is 1. So the total number of moles here is 1. Now, if we are to substitute values, we are going to get this to be mole fraction for PCl3 is 0.09, multiplied by the mole fraction for Cl2 is 0.09 also. Now divided by the mole fraction for PCl5 is 0.82. Then multiplied by the total pressure. From the question, you can see that the total pressure is 4 atmosphere. So we have 4. Now if we multiply this, we are going to get our total, our Kp to be 0.00988. That is very, very important, ATM. Okay, now let's see another question here. We have N2O4, that's dinitrogen 4 oxide, is 25% dissociated at 30 degrees Celsius and 1 atm. That's the total pressure. Calculate A, the equilibrium constant for the decomposition, then B, the amount of NO2 that would be attained if there had been 4 moles of N2O4 at the same temperature and pressure. Okay, now this is quite easy. Here is the equation for reaction. Now let's see the solution for this particular question. N2O4, first of all, we can assume, I said at this point in time, you assume. We can assume that the initial concentration is 1 mole. That's for the initial, is 1 mole, and while for here is 0 mole. So that leads us to the equilibrium concentration. Now here, the equilibrium concentration would be 1 minus, because it is dissociated by 20%, 25%. 25% means 0.25. So I'm going to subtract 0.25. When you say dissociated by, that means what is remaining should be 1 minus 0.25. And if this is reducing by 0.25, this will increase by 2 times 0.25. Why is it 2 times 0.25? Because we have 2 moles here. So by 0.25. Remember, you decrease, but here you increase. Okay, so 1 minus 0.25 here is going to give us 0.75. Then 2 times 0.25 here is going to give us 0.5. Okay, now from here we can find the total number of moles. N total is going to give us 0.75 plus 0.5, and that is going to give us 1.25. The total number of moles is 1.25. Okay, so we can now find the Kp the mole fraction. So the mole fraction here for N2O4 is going to be 0.75, the number of moles for N2O4 divided by the total number of moles, which is 1.25, and that is going to give us 0.6. Okay, the mole fraction for NO2 is 0.5 divided by 1.25. Here is going to give us 0.4. Okay, so we can say that my Kp here is equal to, according to the reaction, is equal to the mole fraction of NO2 raised to power 2 divided by the mole fraction of N2O4. Now that's going to give us 0.4 raised to power 2 divided by 0.6. Remember, we are supposed to multiply by the total pressure raised to power the change in number of moles. The total pressure in the question here is 1 atm, so multiply by 1. So at the end of the day, the whole of this is going to give us 0.27. So our value for Kp is 0.27. Now look at the next question here. The next question, we are asked the amount of NO2 that would be attained if there had been 4 moles of N2O4 at the same temperature and pressure. Now if this guy was 4 moles, it's very simple, just multiply. If you notice, while it was 1 mole, this increased by 0.5. So for 4 moles will simply be 4 times 0.5, and that is going to give us 2. Thank you.